Well, good afternoon, BC Calculus students. This is my third attempt at trying to get a video that will have both audio and video at the same time. So anyway, that's why the delay. But anyway, I think maybe I figured it out and we can go from here. So hope you're having a great summer, and I hope you're having no trouble getting this incorporated a little bit into your summer. We do 10 sections throughout the school year, and for us to get done with all 10, we need to do one of them over the summer. So that's why this summer work. And then so we will be looking at just unit 1, and then going over that again when we get back in the fall. But realize that we won't submit very long in unit 1, probably testing hopefully within the second full week of school. So anyway, just to kind of give you a heads up a little bit, last year we did the first 6 units in the first semester. First semester, remember, is a little bit longer, 10 days longer than the second semester, but it really doesn't matter when the second semester ends, because we have to be done by that second week of March, or second week of May, excuse me, at least to be ready to go for the AP test. So we will probably, even if we can, get a little further than the first 6 units. If you would talk to last year's BC students, they would probably say they felt very rushed at the end. We're going to reverse topics a little bit at the end this year, and be a little more innovative perhaps of what we do in some of that second semester, maybe some independent work a little bit again, we didn't 2 years ago, we did do J-term sessions. Last year we did not. Based upon last year, I would say we maybe need to meet at least a couple times over J-term, possibly to make sure that we're getting done everything we want to get done. So anyway, today I'm going to separate the introduction of limits separate from the introduction to calculus. So as you can see from my screen that I'm sharing with you, calculus basically is the mathematics of change, how fast something is changing at a particular time, at a particular time, and then also. But it has 4 major concepts that I have limits, which you realize you're starting with. And so the limits, that situation is a case where we'll be in unit 1, unit 2, and then we'll use limits in units 3 and 4 to introduce the idea of a derivative. Those of you who've taken physics kind of have a little bit of idea of what a derivative is, but I'll expand upon that as we go on. And then there are 2 types of integrals. Antiderivatives, which is kind of just the opposite of a derivative, kind of like inverse functions a little bit. And then also definite integrals. So 2 types of integrals, limits and derivatives. Limits come throughout the course. Primary emphasis is the first 2 sections, but then you'll see them pop up occasionally as we go on. So calculus, as we started out here, was basically had 3 classic problems that were trying to be solved. Sir Isaac Newton being one of those motivating forces, and Leibniz another. But anyway, the first is that idea of the area under curve, and hopefully this is going to transpire and work the way I think it should. Let's try that again. There we go. And so I want to find the slope of the tangent to the curve at the point, in this case, C. So there's the tangent line, and I want to know what the slope of that line happens to be. Well, we're out of luck as far as slope, because we need 2 points to find the slope. So we realize that now, and by the benefit of those ahead of us, that I could at least approximate that slope of the tangent line by, whoops, I don't like that line at all. Let's try it again. That's a little bit better, maybe. I could approximate that by the secant line. A secant line, again, goes through in 2 points, tangent line in just 1. And so I could determine the slope, change in y over change of x, and come up with then a approximate value, at least, of the blue line, which is the tangent line. I can get a little bit better approximation, perhaps, if I move that point, the magenta point, to the green point, and now try to find the slope of that green line. Again, it's 2 points, so slope formula works. And I could again determine the slope of that. And it's a little bit better approximation of the slope of the tangent line. Of course, you're thinking to yourself at this point already, I'm sure, well, why don't we move that point a little bit closer even to C and see where that turns out to be. And I'm better, only slightly maybe, but if I get very, very close to C, so as X gets close to C, and I use that idea of a limit, then I can basically say the limit of basically here f of x, let's do it this way, let's do f of x minus f of c over x minus c, which is just that limit, that is going to be the slope of the tangent. And you'll notice that that is, those of you who have done some previous work will basically recognize that as basic the derivative formula. Okay, the second formula, or second idea that was probably at the roots of the calculus then, was finding the area of the curve. So we know if it were just a geometric shape, I could divide it into other geometric shapes and come up with an approximation or the exact value of the area of the curve. So one way I might do that would be think in terms of a rectangle from A over towards B, and the area of that rectangle would approximate then the area of the curve. Not exactly, not a very good approximation probably. I could come up with better, for sure. Let's do that. That's obviously an underestimate. I could perhaps have an overestimate. Come up with this rectangle. And that, of course, would be an overestimate of the area under the curve, but it would still be an estimate, not a very good one. So the question might be, well, some of you are, again, thinking, well, why use a rectangle only? Could I possibly use maybe like another geometric shape, a trapezoid? And now I'm getting pretty close to what that actual area under the curve might happen to be. Well, it turns out that we do that even a little differently than what I've just done. We look at dividing that into a series of rectangles. And I don't need to draw all of them in here, perhaps, but I think you know what would be the case here. Let's do two more, maybe, anyway. Oops, the same color. And you got the idea, I think, here. That if I add up all those rectangles, that I'm now getting a much, much better approximation. And hopefully you recognize that as I increase the number of rectangles, instead of the 6 that I have drawn in right now, from 6 to 60 to 6 million to an infinite number of those rectangles, they're going to be so thin that the area of that rectangle will be pretty much the sum of those then rectangles will exactly be the area under the curve. As it turns out, this is kind of surprising a little bit, but there is a point that's going to be on that curve. Let me try there is going to be a point on that curve where the exact value of the area under the curve is the area of the rectangle. And that's where the calculus comes in that we're going to study, and how to find that particular point, or then how to find, in essence, then when it goes to a definite integral, as we have here, that we can find then the integral of that function from a to b of f of dx as the antiderivative of f of b and minus f of a. Now, don't be overwhelmed by everything I'm giving to you. This is all just background material for you. You don't need to memorize this. Some of the terminology you're going to hear repeated soon. So don't be overwhelmed, and you'll have this to go back to and look at again. The last concept then that was kind of the motivating force of the development of calculus was also then finding the length of a curve. So we have the distance formula if it just happened to be a line, but we don't have just a line, we have a curve. And so it's going to have to be done a little bit different way. And again, it's using the limiting process, surprise, surprise. And here then, the scenario would be, if I want to approximate, again, the length of that arc, is what we will call it, I could draw in the secant segment from A to B, and by distance formula, I could come up with what that particular length of the arc would be based upon the length of the segment. I can get a better approximation by using, you guessed it, more segments. So instead of 1, let's try it with 2. And instead of just 2, let's try it with 4. And as I decrease the interval between those secant segments, basically increasing the number of segments, then the sum of those will add up to the exact value, using the limiting factor again, to the exact value of the length of the curve from A to B. So we've tossed around the idea of limits. I'm going to introduce that in the next video. I just want to make sure this one is working like I think it should. And then I'm going to do also another second video for you on introduction to limits, specifically looking at a couple examples from the first 4 days of the notes, of things that I want to make sure you picked up on. And then we'll go from there. So I'm going to stop this now, and then